So replacing some of the specific stuff in there with tokens or with the pieces that link it together. So you see the H token in green has to be the same H token has to duplicate. You see that in the next one, the HB token has to be the same HB token has to belong to first logged on user. So we replace those with variables so they line up, and then we can identify that pattern wherever it occurs. And in fact, that's what we do. We call those behavior specification units. There's a high-level language that makes them very easy to write. If you can write programs for Windows, you can very easily write these. If you're not quite up to writing programs for Windows, you can still write these. Because it's a very simple language geared toward writing these patterns. What happens, of course, is these patterns get compiled into nasty math that you never want to see, and that's okay. That happens behind the scenes. So here's a snippet of one of our BSUs. This is one we use to recognize anti-sandboxing techniques. So if you match this, you're probably malware. We took a lot of these from Paranoid Fish, which is started at the bottom there. Paranoid Fish is an example of various anti-sandboxing, anti-debugging techniques. And you can see we represent a DSU. So there's a DSU somewhere called check for small disk size. There's one called check for mouse movement, etc. And there are rules at the bottom code. If you match any of those, under any conditions, we want to apply this anti-sandbox tag to that piece of code. So we can look for any of this stuff. If Hyperion finds any of this in the call traces, it labels it as anti-sandboxing, and then you can go and look and see what's actually taking place there. And it's easily expanding. We write, in fact, this is a snippet of the larger one. As we discover new kinds of anti-sandboxing, we just add another DSU, another rule to it, and easily expand it. Here's our keylogger detector. In full. So some of those DSU called get key press. It's what you might imagine. It's all the different ways on Windows that you might collect key press. All by file write complete, and that's all the different ways in which you write to a file. We have a couple of things going on here. One is key press has to be the same in both. So we know that the key press that was read is the one that's eventually written. File is part of the file write complete DSU, but we don't care about it here, so we just say we don't care. And the rule says that I have to have B1 followed at some point by B2. Things can happen between the two. Things can happen, and any BSU that matches either one of those is fine. And things can in fact happen in different functions in different parts of the code. But the point being, if I find a new way to read a key press on Windows, I just add that to the get key press DSU, and nothing else has to change. If I find a new way to write it, I add that to the file write, nothing else has to change. If I get interested in people writing key presses to the network, well then I add a new line that says network write complete, and I be sure that the key press is the reference there, and I can add a second rule, which then says B1 followed by presumably B3, and either one of those would catch this. The point is, BSUs are very simple. Essentially simple, but easy to write. They're pretty easy to read. They have a few special symbols in it, but not that much. The dollar signs, or variables, underscores, don't care. You can learn that very easily. They're very extended and they're very robust. So here's a slide example of it. Here's some bytes for an actual piece of malware. This was the malware that was used to attack Oak Ridge National Laboratory back in 2011. That we captured. We can disassemble it. There's part of disassembly. And for those of you who love reading disassembly, this is great. You can structure it. So you turn this into you do call recognition and then destructuring. And so we see if and else is popping up. We see while loops, etc. And that could be helpful. But let's turn it into a call sequence, because that will surely clear it all up once we see the call chain. So there it is, and I'm sure that clears it all up. You can see what's going on: open process, virtual allocation, write process, etc. A lot of stuff in here. But the Hyperion system does the bookkeeping, boils all this down to the one thing you really care about, which is that piece of code is doing process injection. So we get a DSU match, it matches across all the bytes of it, and it says, this piece of code is doing process injection. The first argument, I believe, specifies the process into which you're going to inject. The second one specifies the code you're going to inject. And the third is a delay, which you can hopefully avoid detection. And we get that without actually executing any of it. We match it. We can see which parts of it match that and what's going on. So, again, this is the summary of where we are. PLO8, we've delivered this number of organizations that seem to be working well. We're collaborating with folks at the Applied Physics Lab, at Livermore, at the Pacific Northwest National Laboratory, and at Sandia National Laboratory. The term rewriter that is used in the system is open source, so if you go to GitHub, you can go and grab that. We have about 237 behavior specification units, which allow us to match a very large corpus of malware. We have our own malware corpus here. We work with external organizations that have their own. And so we're routinely looking at our coverage of this. We've got right now 237 BSUs, and we're doing really good matching. And that is about 3,500 lines of BSU, non-comment source statements. So you can see doesn't take a whole lot of writing to get a BSU that's going to be very robust and match a lot of bad behavior. Presently, our top-level malicious BSU finds a whole bunch of good stuff. It finds process injection, service enumeration, key logging, anti-VM, anti-debugging, uploading and downloading behavior, and a whole raft of others that we've introduced to catch all the malware. So that's the status of the system, and I'd be happy to answer any questions you have about it.
This is Dan Trellis at Rapid Labs. I had a question about, maybe you could go a little more detail into the type of testing that was done in National Labs.
So the Hyperion system was selected by the Department of Homeland Security for its transition to practice program. And as part of that, we delivered the source code, the documentation, etc. to Sandia National Lab. And they did a pretty thorough red teaming of it. They red teamed all the technologies that were selected for this program and created a comprehensive support of it. And I read that for you. It's available to folks. David and Nadia had so that report's available if you'd like to see that. They deployed Hyperion on their farm malware repository, and to the best of my knowledge, I talked to Steve Hurd, they were still using it there. So it's been vetted by them. It's been put through its paces at two other organizations. as well, who both done that. I don't think those reports are publicly available, and data taking academy, which means no. But it's been through some pretty significant testing. Like I said, we have our own malware catalog here that we routinely run it over, and at least one of our other partners has a pretty comprehensive malware repo, and they would pretty routinely run it over that and to see what they can catch and discover.
All right, thanks.
Sure. What else can I tell you?
No, nothing else. Thank you. That's good.
So there's one question that came up. Can you describe where this may be in use without going into details of who is actually using it? So I guess I can mention that there's a commercial company, RNK Fiber Solutions, that is licensed to this for commercial use, and they are and I think they're repackaging it to have nice GUIs, etc. I think we didn't tell that much about here.